Welcome, everyone. Today, we will count functions from n elements to k labels in two ways, using Stirling numbers and falling factorials to reveal a fundamental identity. From onto counts to a bigger decomposition of k to the n. The key fact to remember is the number of onto functions from n to a k element set is k factorial times s n k. And this only makes sense in the onto case when n is at least k, because you first partition the domain into k non-empty fibers, then label those fibers with the k outputs.
So Stirling numbers are basically counting partitions, right?
Exactly. Now here is the new twist. Instead of only looking at onto maps, we will group every function by how many distinct outputs it actually uses, meaning the size of its image. Can we take k to the nth power apart into meaningful pieces? This is the basic counting fact. For each of the n inputs, you have k choices for the output, so the total number of functions is k to the n.
So instead of asking whether it is onto, we ask how many distinct values it actually hits?
Yes, and if we can count the j image functions for each j, then summing over j must give back the total. That sum is the decomposition we are building toward. Before we touch Stirling numbers, we need a right algebraic object, the falling factorial, which counts picking distinct labels in order. This product is read as k choices for the first label, then k-1 for the next, and so on, for j total labels with no repeats. The edge cases keep the counting consistent. There is exactly one way to choose 0 labels, and if you try to choose more distinct labels than exist, you get 0 ways.
Injective means no collisions, so this is literally counting one-to-one labelings of j things using k possible labels.
A function secretly creates a partition of the set from 1 to n. If two inputs share the same output, we declare them equivalent. The equivalence classes are the fibers or pre-images of the outputs that actually get used.
Because each used output corresponds to one non-empty fiber, so the number of blocks matches the number of distinct outputs.
For instance, when 1 and 2 both map to A, they land in the same block, while 3 maps to C, so it forms its own block. That is exactly how the function turns the inputs into a partition. Example, all functions f from 1 to 3 into 1 to 3 split by the size of the image of f. This is our checksum. Before we break into cases, make a concrete prediction. How many functions from 3 inputs to 3 outputs have image size 2?
Image size 1 means constant functions, so it makes sense there are exactly 3 of them, one for each output value.
We will justify the Stirling number factor later. For now, treat it as a known coefficient. For image size 2, that coefficient is 3, and the falling factorial 3 falling 2 is 6, so we get 3 times 6 equals 18. Likewise, for image size 3, that coefficient is 1, and 3 falling 3 is 6, so this case contributes 6 functions. Zoom in. Why the size of the image of f equals 2 gives 18 functions? There are 3 ways to split 3 elements into 2 non-empty groups. Pick which element is alone, and the other 2 form the second block.
Because the blocks are distinct objects, choosing which block gets which label is an ordered choice, so we really get 3 times 2.
And now, the number 18 is not mysterious at all. 3 possible fiber patterns times 6 ways to assign 2 distinct output values to those fibers. Now we say the big statement out loud. Every power of k is a sum of falling factorials, and the coefficients are exactly Stirling numbers of the second kind. This equation is just a sentence. Count all functions from n to k by splitting them into groups according to the number j of distinct outputs they use.
So each term is literally, choose how the inputs collapse into j fibers, then choose which j outputs those fibers go to, with no repeats.
This is a built-in reality check. You cannot have a function that hits more than k distinct outputs, so the falling factorial kills those impossible terms for you. Let us watch the identity work algebraically for n equals 3, so you can see that the Stirling numbers are exactly the coefficients that make the polynomial identity true. Here we plug in the Stirling numbers for n equals 3. When you expand the products, everything cancels perfectly, leaving exactly k cubed for every k.
That matches the partitions of 3 elements. Either all together, split into 2 blocks in 3 ways, or all separate.
And this is why I call it the fundamental identity. It is the exact bridge between the world of partitions and the world of polynomials. Now, a pure numbers check. With 4 inputs and only 3 outputs, the j equals 4 term should vanish automatically, and the rest should sum to 81. You see the story numerically. Stirling numbers give 1761, and the following factorials for k equals 3 give 3, 6, 6, and then 0. So the total is 81 as promised.
So 3, 4, 2, and 36 are literally the counts for using exactly 1 output, exactly 2 outputs, or all 3 outputs.
Right? The algebra refuses to count impossible functions. That is one reason following factorials are the perfect language here. Connection to surjections. J factorial times S of nj reappears. This is exactly the onto formula. Partition into j non-empty fibers, then label those fibers by the j targets in all possible orders.
Because if a function uses exactly j output values, then after you rename those outputs as 1 through j, it becomes a surjection onto a j element set, and the only extra choice is which j labels in k those outputs were.
So the whole lecture is one repeated move. Structure first, label second. Stirling numbers count the structure, and following factorials count the labels. Let us synthesize the big idea. We did counting, but we also secretly rewrote one family of polynomials in terms of another family. Think of k to the n as one way to build polynomials in k, and the following factorials as another more combinatorial way, because they encode distinct choices.
So yes, it really feels like change of basis. The Stirling numbers tell you how to rewrite k to the n using the falling factorial basis.
Exactly. Once you see that one-line decomposition, everything clicks. It explains the counting and explains why the algebra has to look the way it does. Exit ticket. Use the identity, then interpret it. Use the Stirling numbers. For n equals 4, they are 1761. So you get k to the 4 equals k plus 7 times k minus 1 plus 6 times k minus 1 times k minus 2 plus k times k minus 1 times k minus 2 times k minus 3.
S of 4, 2 counts the ways to split 4 inputs into 2 non-empty groups, and k falling 2 counts, choosing 2 distinct output labels and assigning them to those groups.
Thanks for watching this. Subscribe to Thinking in Math channel for this and other interesting math topics. And we always welcome your feedbacks. Leave your questions and suggestions in the comments.